Hello everybody and welcome to another FHM Network Academy training video. I'm Sasan Farahman and I'm so honored and grateful to be with you again. After talking about network components in previous video, in this video we will talk about data transmission, which should be addressed in this stage. Let's get started. In previous video we talked about network interface card and some of its characteristics and network media types. But in this video, we will talk about data transmission in detail. In this video, I'm not talking about communication layers, but as an introduction, you need to know a little bit about communication layers. For better understanding, the process of sending and receiving data between computers are split into different abstraction layers. Each layer represents a function performed by protocol, equipment, or software. Data transmission is the process of transmitting data electronically from one place to another. It happens in the lowest layer of sender and receiver side, which is called physical layer. The primary responsibility of physical layer is to convert data into a signal that can be transmitted over a physical medium. The physical layer receives data in the form of numbers from the upside or above layer, which is data link layer, and transmits the signal over a medium. The basic components of the data communication are the message itself, which could be a request or respond to a request. The message is a data or information to be communicated. It may consist of text, number, pictures, sound, video, or any combination of this. Sender and receiver at the two ends of communication channel, or whether to say their network interface cards on the both sides. Sender is a device that sends message. It also called source or transmitter. Receiver is a device that receives message. The receiver must be capable of accepting the message sent from sender. Media or medium or communication channels, which we talked about in previous video. The encoder is a device that converts digital signals in a form that can pass through a transmission medium. The decoder is a device that converts the encoded signals into digital form. Sender and receiver cannot communicate successfully without encoder and decoder. What is signal? Signal is an electromagnetic or light wave that represents data. Signals are used to transfer data from one device to another through a communication medium. Signals are passed between devices in order to send and receive information, which might be video, audio, or some sort of encoded data. When we talked about signals, just think of them as a voltage that's changing over time. Different forms of communication signals are analog and digital. Let's talk about analog signal. Analog signal is a continuous electrical signal in the form of wave. The wave is known as carrier wave. Because a signal varies over time, it's helpful to plot it on a graph where time is plotted on a horizontal or x-axis and voltage on the vertical or y-axis. Looking at the graph of signal is usually the easiest way to identify if it is analog or digital. For instance, a time versus voltage graph of an analog signal should be smooth and continuous. Analog signals range continuously over a specific voltage range. I mean, if you look at this image, you will see voltage level increase smoothly from 0 to the peak, which is 5 in this example, and then decrease to 0 and continue to 5. I mean minus 5. and after reaching the minus peak, it will come back to 0. All this process is known as a cycle. I mean, when a voltage level changes from 0 to positive peak and then moves to negative peak and comes back to 0, a cycle is completed. The amplitude is the peak value of the wave in either the positive or negative direction. The period is the time it takes to complete one cycle of the wave, which is 1 second in our example. And the frequency is the number of complete cycles per unit of time. For instance, we have 2 completed cycles in 2 seconds in this picture. When we use analog signal to send our information, the shape of signal is not complete sine wave or sinusoidal wave all the time. And in most of the case, it's more like these two shapes. We use analog signals in a wide variety of applications. Pure audio signals are analog. The signal that comes out of a microphone is full of analog frequencies and harmonics, which combines to make beautiful music. When you speak, you generate an analog signal, and all devices and applications that somehow related to sound or voice absolutely use analog signal. Examples of analog signal applications could be our voice, audio recording and reproduction, phone line, live sound or amplification devices, older video signal transmission technologies, radio signals and television broadcast signals, or image or temperature sensors. As I mentioned before, our voice is analog. When you speak, you would generate analog signal, and when you hear sound, your ear receives analog signal. As you can see on the picture, when you speak, you would generate signals from 300 to 3400 Hz. When you hear sound, you would receive signal ranges up to 20 kHz or 20,000 Hz, which are all analog signal. Let's talk about digital signal. Digital signals must have a finite set of possible values. The number of values in the set can be anywhere between 2 and a very large number that's not infinity. Most commonly, digital signal will be one of two values, like either 0 or 5. Shape of digital signals look like square wave. Digital signal is a sequence of voltage represented in binary form. The digital signals are in the form of electrical pulses of on and off. These signals are in discrete form. As you can see on the picture, we have just 2 or 3 levels of voltage at a time. For example, in this signal, we have positive 5 volt in this period, and it turns to negative 5 volt, or it could be 0. Unlike analog signals, voltage level in digital signal would not increase smoothly. Actually, we have discrete voltage level, which could be 0, negative, or positive. Now, let's talk a little bit about digital to digital conversion or encoding. Digital to digital encoding is the representation of digital information by a digital signal. When binary ones and zeros generated by the computer, which are translated into a sequence of voltage pulses that can be propagated over a wire. This process is known as digital to digital encoding. Digital to digital encoding is divided into 3 categories: unipolar encoding, polar encoding, and bipolar encoding. Data transmission system sends the voltage pulses over the medium like wire or cable. In most types of encoding, one voltage level represents 0 and another voltage level represents 1. The polarity of each pulse determines whether it is positive or negative. This type of encoding is known as unipolar encoding, as it uses only one polarity. In unipolar encoding, the polarity is assigned to the one binary state. Ones are represented as a positive value and zeros are represented as a zero values. In unipolar encoding, 1 is considered as a high voltage and 0 is considered as a zero voltage. Unipolar encoding is simpler and expensive to implement. Let's talk about polar encoding. Polar encoding is an encoding scheme that uses two voltage levels. One is positive and another is negative. By using two voltage levels, an average voltage level is reduced. Let's compare analog and digital signal. An analog signal is a continuous wave that changes over a time period. But a digital signal is a discrete wave that carries information in binary form. An analog signal is represented by a sine wave, but a digital signal is represented by a square wave. An analog signal is described by the amplitude, period or frequency, and phase, but a digital signal is described by bitrate and bit intervals. Analog signal has no fixed range, but digital signal has a finite numbers, for example 0 and 1. An analog signal is more prone to distortion, but a digital signal is less prone to distortion. An analog signal transmits data in the form of a wave, while a digital signal carries data in the binary form, for example 0 and 1. Example of analog signal could be the human voice, and the example of digital signal is a signal used for transmission in a computer or any digital devices. Let's talk about broadband and baseband definition. The main difference between broadband and baseband is the type of signal that we use for transmission. As you can see on the table, when you use digital signal in our communication, we could say we have a baseband network. Or when you have analog signal for transmission, we could say we have a broadband network. Transmission direction in baseband network is bidirectional, but in broadband network that use analog signal, we have only one direction. Encoding scheme used in baseband network is Manchester encoding scheme while transmitting the digital signal. And in broadband network, we use Manchester encode scheme while transmitting analog signal. Range of signals in baseband network is short, and we just can send our signal in short distance. But in broadband network, we have long distance, and we can send our signals in long distance. Topology used in broadband network is the bus topology as the application, which we will talk in next video. And in broadband, we use tree and bus topology together as the application. The number of data streams transmitted over baseband network is a single data type stream per connection. But in broadband network, we have multiple data streams at the same time, but in one direction only. Medium of transfer in baseband network could be twisted pair cables, coaxial cables, and wires as medium of transmitting digital signal. But in broadband network, we could use optical fiber cable, coaxial cable, and radio waves as medium of transmitting the analog signal. The application of baseband networks is local area networks or LAN networks, and there is requirements of repeaters for transmitting the signal. And the applications of broadband network could be the telephone networks, wireless communication, and satellites. Let's talk about bitrate and bandwidth. As I mentioned before, when a voltage level changes from 0 to positive peak and then moves to 0 or negative peak and comes back to 0, a cycle is completed. As you can see on the picture, it takes 1 second to complete a cycle in both analog and this digital signal. And after 2 seconds, we have two complete cycles. Frequency describes the number of waves that pass a fixed place in a given amount of time. In this signal, we have two complete cycles in 1 second, and after 2 seconds, we would have 4 complete cycles. And in this signal, we would have 6 complete cycles per second, and after 2 seconds, we would have 12 complete cycles. Let's talk about frequency. Frequency is a number of cycles per second in a sine wave or this square wave. Frequency is the rate at which current changes direction per second. It is measured in hertz. 1 hertz is equal to 1 cycle per second. So the more cycle that you complete in a given time, the more frequency you would generate. It is so simple to calculate the amount of data that you could send with your signal through a network. The more cycle you would create or the more frequency you would generate, the more bit rate you would have and the more bandwidth you would need to send your information. It is obvious in this image that in these two signals we have low frequency and these two signals have higher frequency. So the more frequency you would use for your transmission, the more bitrate you would have and the more information you could send to your destination. For the more bitrate, you would need more bandwidth. If you take a look at this digital signal, you would see that we sent 2 bits, one here and one here, in one cycle. And in this middle signal, we sent 4 bits in 1 second. And the bitrate of the signal is 12 bits per second, or 24 bits per 2 seconds. So if the frequency is higher, the more bitrate you would have. With this information, if you take a look at this picture again, you will see that these two signals have higher frequency than any other signals. So the more bitrate you would have, you need more bandwidth to send these signals. And with these two signals with lower frequency, you would have lower bitrate and you would need lower bandwidth. Let's talk about transmission impairment. In the data communication system, analog and digital signals go through the transmission medium. Transmission media are not ideal. There are some imperfection in transmission medium. So the signals sent through the transmission medium are also not perfect. This imperfection called signal impairment. It means the signals that are transmitted at the beginning of the medium are not the same as the signal that are received at the end of the medium. That is what is sent is not what is received. These impairments tend to deteriorate the quality of analog and digital signals, and the consequence of this could be for a digital signal there may occur bit errors, and for analog signals these impairments degrade the quality of signal. There are three main causes of impairments for signals, which are attenuation, distortion, and noise. Let's talk about analog signal impairment, and let's start with attenuation. Attenuation means loss of energy. The strength of signal decreases with increasing distance, which causes loss of energy in overcoming resistance of medium. This is also known as attenuated signal. Amplifiers are used to amplify the attenuated signal, which gives the original signal back and compensate for this loss. Distortion and noise are other analog signal impairment. Distortion means change in the form or shape of the signal, and random or unwanted signal that mixed up with the original signal is called noise. There are several types of noise, such as induced noise, crosstalk noise, thermal noise, and impulse noise, which may corrupt the signal. As I mentioned, distortion or noise changes the form or the shape of signal, which in this case, in analog signal, where we have just amplifier, we cannot make it correct because the amplifier just amplify whatever signal that you send to amplifier. And when the signal or when the shape of signal has changed, the amplifier just amplify the signal with those noise and distortion. And this is why we couldn't fix analog signal when it comes to distortion and noise. In a nutshell, in analog signal communication, we are able to fix attenuation, but not distortion and noise. Let's talk about digital signal impairment. In digital signal communication, we send bits, 1, 0, from sender to receiver. When the attenuation and distortion or noise affect our signal, we have a component which is known as a repeater that regenerates all those bits and create signal like it was in sender. It could fix all of those impairments because unlike amplifier in analog signal communication, we don't amplify the signal here. The repeater read signal and encode all of those signals to bits and regenerate signal again. For example, when a signal received on a repeater decode all of those signals to bits and again turn bits to signal and create standard and clear signal. So we are able to fix all of those attenuation and distortion and noise with repeater in digital signals. And this is why in most communication systems we use digital signals, because we can easily fix impairments and digital signal problems in communication. This is the end of data transmission module. Don't forget to like, share, and subscribe, and I hope you'll find this informative and useful, and I would like to thank you for watching.